The second phenomenon that arises due to non-linearities in amplifier is what we call as gain compression. Gain compression is, imagine we have a certain input to the amplifier, correspondingly there's going to be an output. The input is in, let's say, dBm, the output is going to be in a dBm. We know that the output is in dBm is going to be the input in dBm plus the gain of the amplifier in dB. This relationship is pretty good as long as the input is very low. But what happens when the input power is too high? Let's see what happens. If you have a low input power and if you increase the gain linear, or if you increase the input to the amplifier linearly, the input power linearly, the output is going to be correspondingly increasing linearly. And that holds on up until the input power is up to a certain level. Beyond certain input, the output ceases to increase linearly, but instead it tends to compress. The gain is no more that of a linear amplifier, but it is going to be compressed. And to define how much input power is where it starts to deviate much further from the ideal response is how we define what is called as the 1 dB compression point. The 1 dB compression point. 1 dB compression point is that input power level when the output of the amplifier, that input power level when the output of the amplifier is 1 dB less than that of an ideal amplifier. If it had been a linear amplifier, the output would have been this, which is essentially G plus P in 1 dB. But since the gain has compressed, we have lost 1 dB. So in essence, the total gain that you get is going to be 1 dB less than the gain of the amplifier, which is denoted as G naught here. In other words, this G that we see here is G naught here. And that is going to be compromised by 1 dB at the P1 dB point. When the input is P1 dB, you don't get the total gain G plus P in, but you compromise a 1 dB here. So that is going to be the corresponding amplifier's output. What is interesting to define when you were to compare two amplifiers, which one has a better performance, is to look into what is called as the dynamic range of the amplifier. That means the usable power, input power for a certain amplifier, or realizable output power that you can achieve out of a transistor of an amplifier is what we call as the dynamic range of the amplifier. For that, we would want to define what is called as a minimum detectable signal. A minimum detectable signal which essentially defines the lower bound of the usable range of the output of the amplifier. This defines the lower bound, and you can't use the amplifier beyond the 1 dB output point because the gain has compressed further and the non-linearities are going to be more severe. So essentially this is the range of outputs where the amplifier can be used. And this minimum detectable signal is typically 3 dB more than the noise power. This minimum detectable signal that you want to have the lower bound should be 3 dB, typically is 3 dB higher. That means it's twice the power of noise. It's 3 dB higher than the noise power, which is going to be at the output of the amplifier. So the dynamic range in that sense is going to be the output 1 dB amplifier output at the 1 dB compression point minus the minimum detectable signal at the output of the amplifier. So wider the dynamic range, then better essentially the RF amplifier is.